202. The living tradition. The Africa of the old initiates warns the young researcher, through the mouth of Tirnoboker, sage of Bandiagar, if you wish to know who I am, if you wish me to teach you what I know, cease for the while to be what you are and forget what you know. 203. Plate 8. Eyeball player. The instrument is wooden with steel strings musically. Plate 8.2 and the singer documentation française. 204. Plate 8.3 Griot to miming the fallen Wami Binontet. Plate 8.4 to Cooler musician playing the Ardent Ks, Mali, Note. KO 292. 205. African archaeology and its techniques including dating techniques. Z. Iska and Introduction. When an archaeologist discovers an artifact he usually starts studying it by purely archaeological means such as recording the stratum in which it was found, reading the text found on it, describing its shape, finding its dimensions, etc. The data obtained will then be studied stratigraphically, philologically and typologically, and sometimes important archaeological information may be obtained as regards its date, origin, etc. In most cases, however, the archaeologist may not be able to find any data which answered his question or help him draw any conclusion from the information available. In such cases he is to submit his find to other disciplines for scientific investigation. This investigation is supposed to give useful information about its material, origin, technique of manufacture, date, purpose for which it was used, etc. It might be stressed, however, that this investigation should only be considered as another criterion by which the archaeologist can tackle a particular problem. The scientific evidence should be taken together with such points as stylistic, philological and stratigraphy considerations. One other scientific techniques which may assist archaeology are field surveys of archaeological sites underground without digging and the conservation of the antiques and monuments discovered. The scientific techniques used apply to all archaeology. They apply to African archaeology in the same way as to European, Asian or American archaeology, but sometimes the methods of application differ. The subject is very wide, and therefore we shall deal with the following items in a general way without entering into much laboratory detail. Analytical techniques used in archaeometry. 2 Aims of archaeometric investigation and analysis. 3 Dating techniques. 4 Techniques used in archaeological prospecting. 5 Techniques of conservation. 1. E.T. Hall, 1970. African archaeology and its techniques including dating techniques. Analytical techniques in archaeometry. The techniques of analysis have increased to such a degree that it is sometimes difficult to decide what technique to use on a particular sample to get the information needed. In the following section, this question is discussed from all its aspects. Choice of the method of analysis to be used. Archaeological samples are exceptionally valuable for 2 reasons. The first is that the quantity of material available is usually so small that it may be hardly sufficient for one complete analysis, and if completely used it may not be possible to replace it. The second is that a part of the sample has to be kept for future reference or display. Accordingly, great care has to be taken to ensure that the greatest amount of information be obtained from an archaeometric analysis. The criteria determining the method of analysis to be adopted can be summarized as follows. 2. Availability of material. If the amount of available material is big enough, wet chemical analysis is preferable for determining the percentages of the principal constituent elements in the sample since this method gives the most accurate results. Atomic absorption analysis can be applied to determine the percentages of the alkali metals such as sodium, potassium and lithium. For trace elements and compounds, however, X-ray fluorescence and X-ray diffraction analyses are to be preferred, although they will give results which may be only within 10 to 20% of the correct answer. If only a very small amount of the sample is available and several elements have to be estimated, it can be best analyzed by spectrophotometric methods or by X-ray diffraction methods. If the archaeologist is not willing to provide a piece, however small, of the object, the material can be analyzed by emission spectrometry or by X-ray fluorescence, provided the size and shape of the object permit the apparatus in question to be used. Kind of material to be analyzed. Archaeological materials vary greatly in kind. Some of them are wholly or partly organic such as foods, ointments, resins, oils, waxes, etc. Others are inorganic such as metals, pigments, ceramics, glass, plaster, etc. The HE organic materials are usually submitted to ignition, saponification, solvent extraction, infrared survey, thermal analysis or chromatographic analysis. The HE inorganic materials are submitted to ordinary wet chemical analysis, emission spectrometry, X-ray fluorescence, X-ray diffraction or neutron activation, according to the information needed. 2. IOC. Sit. 207. Methodology and African prehistory. Kind of information needed to save time and expense. The analysis must be performed according to a well-planned program designed in cooperation with the archaeologist to answer specific questions. For example, ancient copper and bronze look superficially similar, so in order to differentiate between them only tin is tested for. This is usually done by treating a small part of the sample with concentrated nitric acid followed by dilution with distilled water when a white precipitate of metastanic acid is formed. This test can even be carried out by the archaeologist himself. Also, lead minerals were used at one time for glazing ceramics in Egypt, therefore only lead need be tested to determine roughly the date at which a glazed object was made. Presentation of results. Since the archaeologists WHO are going to study the results of scientific investigation and use them for their commentary and conclusions are not usually themselves scientists, the results should be presented to them in an easily understandable manner. Thus they should not, for example, be expressed as gram equivalents of a certain constituent per iograms of sample. It will be more helpful to express all results as percentages so that they may be universally understood. Moreover, this will make comparison of results between different laboratories easier. Methods of examination and analysis. In the light of these considerations, we can list the most important analytical techniques used in archaeometry as follows. Microscopic examination to get a preliminary idea about an ancient material or artifact. An examination with a simple magnifying glass IOX or 20x is often very useful. The better device for such an examination is a binocular pattern having a magnification of 7x, 10x or 20x and a long working distance between object glasses and focal plane. This latter feature permits observation of the bottom of deep cavities into which magnifying glasses cannot enter. To obtain a clearer idea, the sample can be examined with a compound microscope 100x, 200x, 400x and 1250x with oil immersion. Microscopic examination can be applied for the following purposes. A. Identification. In most cases it is possible to identify a given sample, whether pure or composed of a heterogeneous mixture by studying microscopically its grain size or the crystalline forms of its constituents. B. Qualitative analysis. Techniques are now available for precipitation, dissolution, observation of gas evolution and other processes which can be. 208. African archaeology and its techniques including dating techniques. Carried out on a minute part of the sample. 3. For example, if a small part of the sample is put on a slide and a drop of water is added to it, it can be observed whether it dissolves or not. If a drop of silver nitrate solution is added to this solution and a white precipitate insoluble in nitric acid is formed, a chloride anion is present. See quantitative analysis. Microscopic methods are particularly valuable in the quantitative analysis of complex heterogeneous mixtures which are not readily amenable to ordinary chemical methods. For this is usually done by counting the number and determining the size of the different components of a powdered sample. The HE volume percentages of the components in the mixture can be converted into approximate weight percentages if the density of each component is known. 5. Radiography. Radiography is essential in the examination of works of art to detect whether there are any objects stuffed, for instance, inside a wrapped mummy or whether there is any decorative inlay hidden under layers of corrosion. Such information is necessary to decide on the correct procedure to follow in unwrapping mummies or conserving metallic artifacts. Taking X-rays of the royal mummies in the Cairo Museum, for example, revealed that some of even the unwrapped ones still have jewelry which has escaped detection because it lies under thick layers of resin. 6. Plate 9.1. Specific gravity determination. Gold in antiquity usually contained silver or copper. Gold objects are so precious that in most cases no samples, however small, can be spared from them for analysis. Cayley, therefore, thought of applying the method of specific gravity determination, which is a completely non-destructive method, to find out the percentage of gold in artifacts. 7. This method is very easy and is conducted by using Archimedes' law W. If the weight of the object in air is Wgm, and its weight in water is xgm, its specific gravity Sg will W. Since the Sg of gold 1923 is nearly double that of silver 1025 or of copper 89, the presence of small amounts of silver or copper can be detected. Assuming that platinum is absent, that the alloying component is defined silver or copper and that no contraction occurs in alloying, the 3. G. W. Ewing, 1954, page 411. 4. P.M. Kama and C. W. Mason, 1938, page 431. 5. I.M. Colthott, E.B. Sandel, E. J. Meehan and S. Bruchenstein, 1969. 6. J.W. Halpern, J.E. Harris and C. Barnes, 1971, page 18. 7. P.R. Cayley, 1949, pages 73 to 82. 209. Methodology and African prehistory. Likely error in determining the gold content is of the order of I%. Ordinary chemical analysis by wet methods. These methods are indispensable in archaeological work for the study of the material of the artifact as well as for deciding a suitable method for its conservation. They are usually used for the qualitative and quantitative analyses of mortars, plasters, corrosion products of metallic artifacts, foodstuffs, cosmetic materials, refuse of embalming materials, etc. The description of the methods used for such analyses is not included in this work. All chemists working in the field of archaeology are well acquainted with them. They are described in detail in analytical chemistry textbooks such as those of Colthott /8 for inorganic materials, and in the work of I.F. Thunder 9 and Strauss 10 for organic and inorganic materials. Iron objects discovered at Niantic and dating from about the 13th to the 15th centuries of our era have been chemically analyzed and proved to contain copper, phosphorus, nickel, tungsten, titanium and molybdenum as impurities probably present in the ores used. 11. Emission spectrometry. This technique is used for the analysis of ancient bronzes, ceramics, mortars, pigments, etc. There are several factors which make emission spectrometry particularly useful when compared with other methods of trace analysis. The sensitivity achieved is generally adequate and it permits the detection of a high proportion up to 20% of most of the elements present. Moreover, all the proportions of the elements present in the sample can be recorded by lines on a photographic plate in one exposure and so provides a permanent record which can be referred to at will. The NEW variation in emission spectrometry has been provided by the development of the laser milliprobe spectrometer. 12. Spectrographic analysis of the naturalistic Nigerian effect bronzes showed that they are made not of bronze but of brass. 13. Atomic absorption analysis. This method is suitable for samples of any inorganic material such as metals, cements, solders, glass, glaze, salts, etc. The advantages of this method in archaeometry are that a high degree of accuracy can be achieved, about 1% error using samples of 5 to 10 meters G, that major, minor and trace elements can be determined in the same sample, and that the technique is 8. I.M. Colthott, E.B. Sandel, E. J. Meehan and S. Bruckenstein, 1969. 9. N. Farad and Z. I. F. Thunder, 1971, pages M. 15, Z. I. F. Thunder, 1961, Z. I. F. Thunder and A. E. Shaheen, 1964, A. Zaki and Z. I. F. Thunder, 1942. 10. F. H. Strauss and A. E. O'Donnell, 1972, pages 1 to 16. 11. A. Mucher and E. Notzak, 1974, page 96. 12. E. T. Hall, 1970. 13. F. Willett, 1964, pages 81 to 3. 210. African archaeology and its techniques, including dating techniques, the standard one, so that inter-laboratory comparisons can be made with confidence, as the possible sources of experimental error can be more easily controlled. 14. X-ray fluorescence. Excitation of a specimen by X-rays provides a useful method for analysis. The principle is that when an atom is bombarded with X-rays of high energy, an electron is removed from an inner orbit of the atom, and the vacancy thus created is filled by an electron from an outer orbit. The He difference in energy between upper and lower level appears as secondary or fluorescent X-rays characteristic of the element composing the specimen. Since the depth of penetration of the X-rays is limited, this method can only be used on the surface of objects, and accordingly it would only be suitable in the analysis of such objects as glass, faience and pottery glazes, obsidian and most kinds of stone. Ancient metal objects, however, suffer depletion, since the less noble metals partly migrate towards the surface, and therefore the surface analysis of such objects by this method may give very different results from that obtained if the whole object were analyzed. 16. Neutron activation analysis. In this technique a group of samples and chemical standards of known composition are placed in a nuclear reactor and irradiated with thermal energy neutrons. SOME or the isotopes so produced will have suitable half-lives and will emit Y rays. Since each radioisotope emits Y rays having wavelengths characteristic only of that isotope, the analysis of these rays enables us to identify the elements present in the specimen and to determine the concentration of both the main elements and the trace elements in it. Neutrons and Y rays have a much greater penetrating power than X-rays. This allows an analysis from a greater thickness of specimen and hence decuperification effects in metals can be ignored. 17. In performing such an analysis, however, it has to be borne in mind that if the specimen has to be returned to the museum, the residual radioactivity must decay to a low level in a reasonable time. Radiosilver, for example, has an isotope of 225 days half-life, and if too high an irradiation dose is given to a silver object it might not be possible to return it to the museum for hundreds of years. 8. In such a case, therefore, an extremely small amount of the silver is taken from the specimen by rubbing it against a small disk of roughened quartz. This street quartz is then irradiated in the reactor. 14. 8. E. 8. Werner, 1970. 15. I.M. Kolthoff, E. B. Sandel, E. Chamey and S. Bruckenstein, 1969. 16. E. T. Hall, 1970. 17. LOC. Sit. 18. LOC. Sit. 211. Methodology and African prehistory. And analyzed for silver, gold, copper, antimony and arsenic in the usual way. This method has been applied very recently to the study of glass beads in Africa and archaeology, subjecting them to 2 neutron activations. The He first bombardment was brief and the samples were analyzed immediately after for short-lived isotopes. The He second bombardment was intense and continued for 8 hours. The samples were set aside for a few days and analyzed for medium-lived isotopes, set aside again, and later analyzed for long-lived isotopes. 19. A survey of the many applications of this technique in archaeometry is given by Sayer and Myers. 20. Aims of archaeometric analysis. The most important aims of scientific investigation and analysis in archaeometry are the following. The exact identification of materials. The exact identification of archaeological material is essential to ensure an accurate description because a significant interpretation of the object concerned usually depends on knowing the exact nature of the material it comprises. Errors of identification are, unfortunately, not infrequent in the older archaeological literature and have caused a lot of perplexity. Copper is sometimes confused with bronze, although the discovery and use of bronze posits a certain cultural revolution. Bronze is sometimes confused with brass, and hence a wrong conclusion may be reached as to the date of the object since brass was first made at about the middle of the 1st century before our era, while bronze had been known and used some 20 centuries earlier. 21. Since most inaccurate identifications arose from a dependence on visual appearance, it must be emphasized that the identification of archaeological material must be based upon chemical examination or X-ray diffraction analysis so that misleading interpretations may be avoided. Translation of UNKNOWN ancient words. Accurate identification serves sometimes to clarify the meaning of unknown words. For example, 2 pots were found in the tomb of King or Aha First Dynasty, about 3100 before our era at Saqqara in Egypt. On each of these pots is written in hieroglyphic the word Sirat whose meaning was not known. Chemical analysis showed that the contents were chitin. 19. C. C. Davison, 1973. 20. E. V. Thayer and P. Myers, 1971. 21. E. Archeli, 1948. 212. African archaeology and its techniques including dating techniques. It was therefore concluded that sirit meant cheese. 22. Another example is the hieroglyphic word bekan written on some stone statues. Since the stone had been identified as greyackerschist in some other cases and this word was used in texts connected with Wadihmmt, it was concluded that most probably bekan meant the greyacker of Wadihmmt. 23. Detection of the sources of materials. The presence of numerous specimens of material of foreign origin at an archaeological site is a clear indication of the import of such a material through trade or commerce. If the source of this material can be located, then the path of the trade can be established. For example, it is known that obsidian does not occur in Egypt. Nevertheless, it was used in Egypt as early as pre-dynastic times before 3100 before our era. Some objects made of this obsidian were examined and compared with the obsidian found in neighboring countries. It was found to be very similar to the obsidian of Ethiopia, hence it is concluded that it was imported from Ethiopia and that there had been trade relations between the two countries from very early times. 24. Determination of trace elements in pottery by neutron activation or X-ray fluorescence can afford the means of studying trade routes both locally and between different countries. 25. Trace impurities in copper ores and artifacts can help also in establishing the relationship between the artifacts and the kind of ore from which the material of the object was derived. 26. Determination of nickel in an ancient iron artifact affords a means of deciding whether it is meteoric iron or man-made iron, since meteoric iron always contains nickel in the ratio of 4 to 20%. The famous iron dagger of Tutankhamun has been examined for the author by emission spectral analysis and it has been shown that the iron of the dagger contains a good quantity of nickel, thus proving that the iron is of meteoric origin. Finding out a purpose for which a material was used. Sometimes it is difficult to know for what purpose a certain material was meant to be used. In this respect chemical analysis may be of great help. For example, in the tomb of Nefertiti about 1800 before our era which was discovered in the Fayoum in Egypt in 1956, a very large alabaster jar was found to contain 2 to 5 kilograms of a strange material. Chemical analysis showed it to be composed mainly of 48-25% galena natural lead sulfide and 22. A. Zaki and Z. I. Eskandar, 1942. 23. A. Lucas, 1962. Pages 416, 419 to 20. 24. LOC. Sit. 25. I. Perlman and F. Isero, 1969. 26. P.R. Fields, J. Millesteed, E. Hendrickson and R.W. Ramati, 1971. 213. Methodology and African Prehistory. 51-6% resin, i.e. of galena and resin in the ratio of I, by approximately. Such a composition had never been found before, and therefore the reason why it had been put in the tomb was completely obscured. However, on consulting the prescriptions given in the Ebers Papyrus, it was found that prescription No. 400 states, another remedy for the removal of white spots which have arisen in the two eyes, black coal galena and Kedwa resin are ground fine and put in both eyes. From this text and the chemical composition of the material contained in the jar, it was concluded that this was a medicament for the eyes, that Nefertiti most probably had glaucoma in one or both of her eyes and that is why she was provided with a great quantity of this medicament for use in the hereafter. 27. Determination of the details of ancient technical processes. The examination of ancient objects by scientific methods can yield information about the techniques utilized by ancient people in their chemical arts and industries. This can be shown by the following examples. Manufacture of Egyptian blue. Specimens of this blue pigment have been examined chemically, microscopically and by X-ray diffractometry, as well as a similar blue frig which has been reproduced experimentally. These studies proved that Egyptian blue was made in ancient times by heating to 840 degrees C the mixture of sand or powdered quartz, powdered limestone, malachite and a flux of common salt or natron. 28. Microscopic examination of metal objects. Metallographic examination of metal objects can show whether they were produced by casting or by hammering or by a combination of both. For example, The copper staple from the Cheops boat discovered in 1954 behind the Great Pyramid at Giza has been examined metallographically, and it was revealed that the metal has a fragmented dendritic character plate 9.2, thus proving that it had been shaped by hammering. 29. Examination of the refuse of embalming materials. Examination of samples of the refuse of embalming materials discovered in Saqqara, Luxor, and Mataria in Egypt proved that they contain a small proportion of soaps of solid fatty acids which were formed as a result of the saponification of the fats of the body by the action of natron during mummification. From this it was concluded that in the process of mummification such materials had been used for the temporary stuffing of 27. Then. Farad and Z. I. Iskandar, 1971, pages IU 15. 28. The Lucas, 1962, pages 416, 419-20. 29. Z. I. Iskandar, I. 960. 214. African archaeology and its techniques including dating techniques. The body cavities prior to its dehydration in a heap of natron on the bed of mummification. 3 degrees. Glass ferting crucibles. The scientific investigation of some of the remains of a glass factory in Wadi El Natron showed that glass was manufactured in 2 stages in Egypt during the Roman period. The first stage was to prepare the glass frit by heating together a mixture of silica quartz, calcium carbonate and natron or plant ash or both, in a special kind of crucible, the ferting crucible, at a temperature less than 2 degrees C. The clay of which this crucible was made contained a high proportion of sand and finely chopped straw. Such a mixture would produce a highly porous pottery when baked, a characteristic which was clearly intended by the ancient glassmaker so that he could easily release the frit block plate 9.3 by breaking the crucible. So it was used only once. The second stage was to obtain a good quality glass of various colors. The frit blocks were ground into a fine homogeneous powder and divided into small batches. Each batch certain colorant oxides, opacifier or decolorizing agents were added and reheated until complete fusion in order to obtain the kind of glass required. 31. Testing of authenticity. For many years, the historic and aesthetic approach was the only method of judging authenticity. In more recent years great progress in scientific examination has made it possible to judge the genuineness of an object with greater certainty. The most effective scientific methods used for testing authenticity are the following. Examination under ultraviolet light. This technique is particularly useful for the examination of ivories and marbles. Under ultraviolet light different marbles fluoresce different colors, and the surface of ancient marble frequently has a characteristic fluorescent color which is very different from that of fresh stone of the same kind. On this basis also, alterations or repairs in an ancient marble or ivory object or painting, which are not visible in ordinary light, and a white become strikingly conspicuous when the object is scrutinized under ultraviolet light. Similarly, infrared light and X-rays have been found useful in the detection of forgery. 32. Examination of the surface corrosion crust. Ancient metals usually corrode slowly, and a coherent corrosion layer or 30. Z. I. Iskandar and A. E. Shaheen, 1964. 31. S. A. Saleh, A. W. George and F. M. Helmi, 1972. 32. E. R. Gailey, 1948. 215. Methodology and African prehistory. Crust is formed in the course of time. In metal fakes, an artificial crust is usually applied to the surface to give it an ancient appearance. This crust is found to be comparatively loose and can be removed by solvents such as water, ethyl alcohol, acetone or pyridine. Moreover, on copper and bronze objects, this artificial crust will in most cases be composed of one layer and can easily be distinguished from the naturally formed crust which is always composed of at least 2 layers, the inner of red cuprous oxide and the outer of green basic copper carbonate or basic sulfate or chloride. Such an arrangement cannot be intentionally imitated in such a way as to deceive an experienced chemist in an archaeological museum. Analysis of the material of the object. A very striking example of such a technique is the analysis of the core of ancient Egyptian faience. While the core of the genuine ancient Egyptian faience is made up of quartz frit, the body core of modern faience fakes is usually made of kaolin or china clay, and this affords a quick and reliable test of authenticity. Another example is that ancient metals contain certain impurities such as arsenic, nickel, manganese, etc., since the ancient metallurgical techniques did not adequately refine metals. Therefore, if a small sample taken from an inconspicuous place on the artifact is analyzed by neutron activation or X-ray fluorescence and proves to be free of such trace elements, the object is most probably a fake. Identification of pigments and media in painting by microchemical techniques. It is possible to identify the pigments used in a painting with reasonable accuracy. If the pigment proves to be among the recently discovered ones, the painting is a fake. For example, the painting, purportedly a 15th century profile portrait, was examined by Young. The blue pigment proved to be synthetic ultramarine, which was not discovered and used as a pigment before the 19th century. The white pigment was found to be titanium oxide, which was not used in painting before 1920. The HE painting proved, therefore, to be a forgery. 33. Examination of surface patina and polish. Most stones acquire in the course of time a surface patina or desert varnish. This is formed as a result of the migration of iron and manganese salts to the surface, where they are deposited as oxides which form the kind of epidermis or patina. Since this patina forms a part of the stone, it is coherent to the surface and cannot easily be removed by washing with a neutral solvent or by scraping. It is consequently possible to distinguish an authentic aged surface from a freshly carved surface, even if it is artificially patinated. Apart from the naturally formed patina, the marks of ancient carving and polishing may afford means of deciding authenticity. These marks still show themselves as irregular intersecting lines under the surface patina of stone. Door 33. W. J. Young, 1958. 216. African archaeology and its techniques, including dating techniques. Metal and are easily distinguishable from the regular parallel lines due to recent polishing, since the ancient people did not use coarse files in carving, nor fine files or emery paper for polishing. Testing the thermoluminescence of pottery. In pottery, as well as in the soil in which it is buried, there exists a very small percentage of radioactive elements. These emit a certain amount of radiation which causes an accumulation of electrons over thousands of years in the body of the pottery. Heating such pottery to a temperature above 500 degrees C, the accumulated electrons are released as thermoluminescence, which varies according to the age of the pottery. Thermoluminescence, therefore, provides museum curators with very powerful evidence as to whether a pottery object is imitation or genuine. The sample for testing is obtained by drilling a small hole in an inconspicuous position, and the powder obtained is heated to above 50 degrees C in darkness. If thermoluminescence is produced, the pottery is genuine; if not, it is a forgery. 34. Dating techniques. Science affords several techniques for dating ancient materials. The main techniques used in this respect are the following: ROUGH dating by archaeometric analysis, and analysis of specimens of the same groups of materials, such as mortars, glass, fions, metals and pigments, but of different known dates, may give results which can be used as a clue to indicate roughly dates for other specimens of unknown dates. The following examples illustrate this. Dating by analysis of glass beads from West Africa. Dichroic acorate beads, which appear blue by reflected light and greenish yellow by transmitted light, were subjected to X-ray fluorescence analysis. They were found to fall into two groups. Group A was found to be much poorer in lead, less than 0.05%, and arsenic less than 0.205% than Group B, in which lead is about 27% and arsenic is about 2%. There is also a smaller difference in the manganese content. Group A 0.23 plus or minus 0.1%, Group B about 0.05%. Other elements determined were iron, cobalt, copper, zinc, rubidium, strontium, tin, antimony and barium, but no striking differences were noted. Group A beads are found in West Africa in relatively old inland sites 430 to 1290 of our era, while Group B is found only in younger contexts. The finding of such beads in a tomb or a stratum can afford, therefore, a means for indicating roughly its date. 35-34. M. J. Aitken, 1970. 35. C. C. Davison, Hardy. Guy Ake and J. D. Clark, 1971. 217. Methodology and African prehistory. Dating of Southern African paintings. By analysis of albumin outbinders, paintings may be dated by determining the number of amino acids in their albumin outbinders after hydrolysis. This method has been used to determine the ages of 133 rock paintings from southern Africa with 20% accuracy. The White Lady of Brandberg proved to be 1200 to 1800 years old. Limpopo paintings ranged from 100 to 800 years in age. Drakensberg samples ranged from 60 to 800 years in age. The number of amino acids which could be identified decreased with the age of the painting from 10 in the binders 5 to 10 years old to 1 in materials 1200 to 1800 years old. 36. Dating by analysis of mortars. Analysis of various mortars used in Egypt showed that lime mortar was not used before the time of Ptolemy I 323 to 285 before our era. 37. The NY monument whose bricks or stones were bound together with lime mortar would, therefore, belong to a period later than 323 before our era. Radiocarbon dating. Basic principle. When cosmic rays strike the atoms in the upper layers of the atmosphere, they cause them to disintegrate into tiny fragments, among which is the neutron. The neutrons produced bombard the most abundant atom in air, namely nitrogen of mass 14, converting it into a carbon of atomic weight 14. This newly formed carbon-14 is radioactive and combines with oxygen from the air, forming I4C02, and is mixed with the ordinary carbon dioxide, which contains mainly non-radioactive carbon atoms of masses 12 and 13 in abundances of 99 and 1% respectively. This carbon-14 enters into the plants together with the ordinary 2C02 and 3C02, forming their tissues by the process of photosynthesis. Since animals feed on plants, all the living animal and vegetable world should be very weakly radioactive owing to the presence of a minute proportion of carbon-14, approximately 1 atom of carbon-14 to a million atoms of ordinary carbon. Atmospheric carbon dioxide also enters the oceans as dissolved carbonate, so this too should be weakly radioactive and any shells and deposits formed from it. 38. At death, the ancient organic matter is supposed to have had the same radioactivity as living organic material at the present time. But after death isolation occurs, i.e. further uptake or exchange of radiocarbon would cease and the carbon-14 starts to decay, or as Professor Libby expressed it, the radiocarbon clock starts ticking. 39. The radioactivity of an ancient sample. 36. E. Dettinger, 1971. 37. 8. Lucas, 1962, pages 416, 419-20. 38. M. J. Aiken, 1961. 39. W. F. Libby, 1970, pages 1-10. 218. African archaeology and its techniques, including dating techniques, is measured and compared with the activity of a modern sample. It is possible, knowing the half-life of carbon-14, 40, to calculate the age of the ancient sample by applying the radioactive decay equation. Materials most suitable for radioactive dating. The materials suitable for this technique must be of organic nature, such as wood, charcoal, bone, leather, cloth, grasses, foodstuffs, shells, etc. But the best suited are those derived from plants growing within a single year, such as reeds, cereals, grass or flax. The samples should not be treated with any chemicals when first collected, and should be put directly into glass containers or nylon bags to eliminate contamination with any new organic matter. The HE procedure in general consists of 4 steps, namely, purification of the sample, combustion, purification of the carbon dioxide gas obtained and, finally, counting of the particles emitted. Results and prospects. In order to test the accuracy of this method, a comparative study of historically well-dated samples and radiocarbon dates has been undertaken. For since the oldest and best understood historical sequence is the chronology of Egypt, it was decided internationally to measure the radiocarbon content of a long series of archaeologically precisely dated Egyptian samples belonging to the time period from the First Dynasty about 3100 before our era to the 30th Dynasty 378 to 341 before our era. The dating was carried out in several laboratories at the same time using both 55-68-year half-life as well as the newer and physically more correct value of 5730 plus 40 years. The HE results of these laboratory tests showed that radiocarbon dates, using the 5730-year half-life, match well with the historical chronology back to the time of King Senusret III, i.e. to about 1800 before our era, but there are wide divergences between the two dates for the earlier samples. If, however, the correction factor, the Spliversus correction, is applied to the samples which antedate 1800 before our era, the results will be found to be in agreement with the archaeological dates to within 50 to 100 years at most. 42, for example, reeds taken from the mastaba of Ka at Saqqara, 1st dynasty, were dated in the British Museum Research Laboratory. The radiocarbon date obtained is 2450 plus 65 before our era. Then applying the correction factor, its date was calculated as 2928 plus minus 65 before our era, which is very close to its historical date, 2900 before our era. 43. 40. The HE period of carbon-14 duration of the disintegration of half of the radioactive body was first assessed at 5568 years. Later, more precisely, at 5730 plus 40 years. 41. R. Berger, 1970, I.E.S. Edwards, 1970, H. N. Michael and E. K. Ralph, 1970, E. K. Ralph, H. N. Michael and M. G. Hahn, 1973. 42. R. Berger, 1970, H. N. Michael and E. K. Ralph, 1970, E. K. Ralph, H. N. Michael and M. G. H. N. 1973. M. Studer and H. E. Suits, 1966. 43. I.E. S. Edwards, 1970. 219. Methodology and African prehistory. The speculation at the moment is whether the main deviation is due to a weakening of the Earth's magnetic field 44 or two variations in the intensity of the solar wind which fends off cosmic rays. 45. Moreover, the actual half-life of radiocarbon is not entirely certain. Some other causes are under consideration and research is being carried out in many laboratories on this problem. If all these questions were answered, it would be possible to date with greater precision on periods earlier than 1800 before our era. Until then, conventional radiocarbon measurements of ancient organic samples from these periods must be corrected as indicated above. Potassium-argon dating. The limitation of radiocarbon dating to about 70,000 years leaves a long gap in the chronology of biological and geological development, extending from this date to about 10 million years earlier. For this very early period it would be possible to apply established geological radioactive methods based on the rates of change in certain substances such as the change of uranium-235 to lead-207 which has a half-life of 710 million years, or rubidium-87 to strontium-87 which has a half-life of 13,900 million years. The He gap can be filled to some extent by applying the technique of potassium-argon dating. 46. In fact, this method is used particularly for the dating of lower geological ages, but by using large samples of a substance of comparatively small grain size but not less than 100 Y and containing only little atmospheric argon, it is possible to apply it to comparatively more recent periods which may even overlap with carbon-14 results. 47. Basic principle potassium SWE find it now in nature contains 93 to 2% potassium 39, 6 to 8% potassium 41 and OOI 18% potassium 40. At the time of the formation of the Earth the abundance of potassium 40 was about 0 to 2% but most of it decayed into two daughter products, calcium 40 and argon 40. Since potassium 40 has a very long half-life 1330 million years a small amount of it amounting to 0.0118% is still present. For 100 atoms of potassium 40 which decay, 89 become calcium 40 by beta decay and 11 become argon 40 by capture of beta particles. Argon is a gas and is retained between the grains of the mineral. 48. The potassium-argon dating has found a number of applications for the following reasons. 44. V. Buka, 1970. 45. S. Z. Lewin, 1968. 46. M. J. Aiken, 1961. 47. W. Gentner and H. J. Lippold, 1963. 48. LOC. Sit. E. I. Hamilton, 1965. 220. African archaeology and its techniques including dating techniques. A. Potassium exists in the Earth's crust to the extent of 2 to 8% by weight and hence it is one of the most abundant elements and is contained in almost all materials. The argon-40 can be measured more easily than most other elements even in very small concentrations. The half-life of potassium is long enough for appreciable amounts of argon-40 to be formed in potassium minerals within geologically interesting periods. By measuring the concentration of the radiogenic argon-40 and the total content of potassium of a mineral, it is possible to determine the age of the mineral by applying the radioactive decay equation. 49. Problems to be solved by potassium-argon dating. Potassium-argon dating has recently been applied to calculate the in situ first-order rate constant for the racemization of aspartic acid in old bones. Once the racemization reaction has been calibrated for a site, the reaction can be used to date other bones from the deposit. Ages deduced by this method are in good agreement with radiocarbon ages. These results provide evidence that racemization is an important chronological tool for dating bones which are either too old or too small for radiocarbon dating. As an example of the application of this technique for dating fossil MBN, a piece of Rhodesian MBN from Broken Hill, Zambia, was analyzed and tentatively assigned an age of about 10,000 years. Degrees The problems which can be solved with the help of potassium-argon dating of the Pliocene and Pleistocene periods include the determination of an absolute time scale dating the origin of MBN, the coincidence in time of fossils in the different parts of the Earth, and the origin of tektites as well as other special geological problems. Potassium-argon dating has been used to determine the ages of the basalt layers and the overlying tuff layers in Old Away with the aim of determining the absolute age of the Zinjanthropus remains which were found near the bottom of bed of tuff. Kurt and Everrounden concluded that the basalts at Old Away are at least 4 million years old, but are unreliable for dating purposes because of chemical alterations visible in thin sections of all dated Old Away basalts except those associated with the older pebble tool industry. Gentner and Lippold comment on the different results obtained by reporting that as no further inconsistency exists between the dates of the overlying tuff and the basalts, an age of 2 million years for Zinjanthropus seems to be possible. 51. Archaeomagnetic dating. In order to give a simplified idea about this technique, we shall deal with the following items. 49. W. Gentner and H. J. Lippold, 1963. 50. J.L. Bada, R. 8. Schroeder, R. Prosch and R. Berger, 1974, page 121. 51. W. Gentner and H. J. Lippold, 1963. 221. Methodology and African Prehistory. Paleomagnetism. This term signifies the study of the remnant magnetism of archaeological remains. It is based on the fact that the magnetic field of the Earth is changing continuously in direction and intensity. Observations over the past 50 years indicate that the changes in direction are at the rate of 0 to 2 degrees of longitude westward per year. 52 Archaeomagnetic investigations based on the measurement of remnant magnetization in baked archaeological objects and in rocks show that the Earth's magnetic intensity during the past 8,500 years had its maximum around 4,00100 before our era when the field reached 6 times its present intensity, and its minimum around 4,000 before our era when the field dropped to around 0.6 times its present intensity. 53 These effects or variations in direction and intensity are termed secular variation. This is of the regional nature, and it is the basis of magnetic dating since the changes in the Earth's magnetic field leave their record in baked pottery as thermal remnant magnetism (TRM). The application of the TRM for archaeological dating. For magnetic dating of baked clay which has remained in situ since firing, it is necessary first to establish the behavior of the geomagnetic field direction by measurements on archaeological structures of known age for the region in which dating application is to be made. The HE results are plotted in a curve showing the secular variation in that region over a long period of time. Knowing the direction of the magnetic field recorded in a baked clay of unknown date in the same region, it is possible to determine its date of firing by reference to this secular variation curve. The most suitable samples for magnetic dating are baked clays from kilns, ovens and hearths which have remained in their original places until now. Since a portable magnetometer has not yet been produced to measure their geomagnetic field direction in situ, samples must be removed for measurement in a fixed magnetometer in a laboratory. It is essential that each sample should be marked with its original orientation to serve as a reference for the direction of its OWN remnant magnetism. This is done in practice by capping it with plaster of Paris, taking care that the top surface is horizontal and marking the direction of the geographic north on the horizontal surface of the mold before the sample is detached. In this way the ancient declination d and the ancient angle of inclination I can both be determined. 54 to compensate for anomalies, 6 or more samples should be taken, preferably from different parts of the structure and in a symmetrical pattern. 55. 52. M. J. Aitken, 1961, R.M. Cook, 1963. 53. V. Buca, 1970, V. Buca, 1971. 54. M. J. Aitken, 1970. 55. R.M. Cook, 1963. 222. African archaeology and its techniques including dating techniques. Archaeomagnetic results for D and I have been obtained for England, France, Japan, Iceland and Russia. As far as I know, the method has not yet been tried in Africa. It is hoped, however, that it may be applied very shortly for dating in Africa and archaeology, especially since the method has been appreciably improved in the last few years. Thermoluminescent dating. Thermoluminescence is the emission of light when a substance is heated. It is quite different from red-hot glow and it is due to the release of energy which has been stored as trapped electrons in the heated material. In all pottery and porcelain contain small proportions of radioactive components, a few parts per million of uranium and thorium and a few % of potassium. In addition, there are radioactive impurities in the surrounding burial soil, as well as cosmic rays which can penetrate the soil to the burial place of the pottery. These will emit radiations which will bombard the crystalline materials such as quartz in the pottery. The He resultant ionization will produce electrons which may become trapped within the crystal structure. These electron traps are metastable, and when the sample of the ceramic is heated the traps will be dissipated and the excess energy appears as a photon of light. The He intensity of this light toward thermoluminescence will be directly related to the age. It is also dependent on the particular thermoluminescence constituents in the pottery sample and surroundings. 56 By measuring the amounts of uranium, thorium and potassium present in the pottery fragment and in the soil, the radiation dose received by the fragment each year can be calculated. In principle the age is then directly calculated using the following relation, 57. Accumulated radiation dose age equals dose per year. Accuracy of results and prospects at present an absolute accuracy of around plus or minus 10% is achieved. This is somewhat poorer than is obtainable with radiocarbon dating, and is attributed to many difficulties which have arisen such as the uncertainty about the burial circumstances, and the uncertainty about the degree of wereness of the burial place which affects the dose rate due to radioisotopes in the pottery fragment. It is hoped, however, that further research will solve such difficulties but, for various practical reasons, it is not likely to improve this result to a greater precision than plus or minus 5% error. 58. 56. M. J. Aitken, 1970, E. T. Hall, 1970. 57. M. J. Aitken, 1970. 58. LOC. Sit. 223. Methodology and African prehistory. Despite this low accuracy, however, this technique has the advantage over radiocarbon dating that pottery is much more abundant in more archaeological sites than organic material, and that the event dated is the actual firing of the pottery, whereas in the case of radiocarbon dating of wood or charcoal the event dated is the cutting of a tree and not the date of using it in antiquity. This technique will have a very important application in Egypt. Neolithic and pre-dynastic cultures in Egypt have so far been mainly dated by the types of pottery characteristic of these cultures according to the sequence dating system first invented by Flinders Petrie. 59 and OW. It will be possible by thermoluminescence dating to determine the absolute dates of these cultures. Techniques used in archaeological prospecting. The basic aim of scientific techniques in field prospecting is to discover information on buried archaeological sites either before or instead of excavations. This saves much time, effort and expense. Archaeological prospecting by scientific methods includes the following techniques. Hair photography. This technique is basically used for the recognition of a feature by its geometrical pattern. It has two main applications. The first is that it gives a more distant and thus a clearer view, fitting the individual surface traces together into more meaningful patterns. 60. The aerial photographs can then be used to identify the areas which have to be excavated to give a complete picture of the whole archaeological complex. This method has been applied for the study of the Karnak temples at Luxor in Egypt, where the area of the site is about 120 hectares. The second application is that it reveals the existence of buried archaeological structures in cultivated lands from crop marks. Crop marks result from different moisture conditions in the soil. The crop above a buried stone wall will be weak, showing up as a lightened line, while above a buried ditch the crop is richer and therefore darker in appearance. From the geometrical layout of these traces, the buried structures can be recognized and excavated. 61.